right, so we're doing atomic structure and periodicity. In this unit, we're going to start today looking at the structure of the periodic table by introducing the concept of orbitals. We already covered all of this stuff yesterday. Bohr model. What was the Bohr model again? Hydrogen is an example of what was a primary Bohr model, but what was special about the Bohr model? What stood out? Showed levels as, what were the circles? Orbitals were concentric circles around the nucleus, and we know that's not true. So instead, we're going to be looking at what an orbital really is. And there's some crazy math involved with this. I heard you guys, my little nerds, talking about how you hate quantum because there's so much math. Yeah. Well, it is actually. The entire concept of quantum chemistry is based on the math derived to find it's basically the probability of where an electron is going to be located. Heisenberg uncertainty principle is the basis of this. I'm sure you've seen a bunch of jokes all surrounding Heisenberg, like an electron was speeding and the cop stopped him and said, yes, that's why the Breaking Bad Heisenberg thing, everything they use in Breaking Bad actually has a deeper meaning. But do you remember the joke? I don't remember it. It was, you have to be on the, no pressure. So
I don't remember the joke like specifically, but I think the atom is feeding and like the cop pulls him over and he's
an electron.
An electron was feeding, the cop pulls him over and it's like, oh gosh. No, he's like, sir, you were speeding. It's like, how do you know like where I am?
How do you know that I wouldn't be here or I'm not here? Or do y'all remember it? Oh, okay. We're gonna look it up. Anyway, this little cartoon is also, referencing the whole concept of you really can't know the location and the momentum of an electron at the same time. I like to think of orbitals, which are the locations that we're going to find an electron about 90% of the time. I think about the ceiling fans. How many of you have ceiling fans above your beds? Okay. Not anymore? What happened? It fell? All right. That must have been fun. I hope you weren't under it when it fell. So when you look up and you see the blades moving, do you see how you can kind of detect a circular shape made? It seems like the blades are filling that shape. Is it really easy for you to pinpoint the location of that fan blade at that one moment? No, not really. It's kind of tough. And that's kind of the concept here, except that fan blade, those blades are more two-dimensional. Think about, a spherical orbital, an s orbital, the electron just filling up that space. Okay, and that's what I want you to think of an orbital as. There's no walls of an orbital. It's just an area in space that the orbital happens to occupy in the majority of the time. There's a lot of visual representations out there. There's these really fancy ones, these radial probability distributions. Like, we can look at this, and we can plot how far away. What? Okay, hold on. Let me finish this, and you can tell the joke. From the distance from the nucleus, you can do a plot of where you find electrons, and depending upon how far away, you might see multiple peaks. So we might see a peak here, and then as this continues, you might see a peak later on. And this might be the 1s orbital, and then this might be the 2s orbital. So all these funny, crazy diagrams, which you're not responsible for, just lead to the important things about orbitals, which are basically listed here. So Alyssa found the joke, so go ahead and tell the joke.
Heisenberg is out for a drive when he's stopped by a traffic cop. The cop says, "Do you know how fast you were going?" Heisenberg replies, "No, but I know where I am."
Ha ha ha. Okay, that was good. All right. So, difficult to define precisely where an electron is. We know that we have a 90% chance of finding it in one of our established orbitals that we're going to talk about today. So let's go and do a big-time review on the periodic table. We're going to break it down first by level or shell. There's a lot of different ways to say the same thing. The shell or level is indicated by these numbers. It's usually an n. That's the principal quantum number. That's the level that we can find an electron. When we're in this unit, it's important for you to think of this table as building of electrons from low energy to high energy. Yeah, I know this is protons as well, but in neutral atoms, for every proton, we're adding that one electron. So think of this as a building of electrons. So y'all remember energy levels 1, 2, 3, 4, 5, and so on, right? And according to the quantum theory, the mathematical model that fits all of this, these theoretically should go on to infinity. There really should be an infinity number of energy levels. Now, these energy levels are broken down into sublevels, also known as orbital types. So let's name our blocks, and then we'll talk about how it's a sublevel. Who remembers this block? This is the S block, right? Did someone say P, really, Dwight? I just called you out on mic. This is going to be for eternity, because I'm not taping again next year. So for at least 2 years, people are going to know that Dwight thought the S's was the P. All right, what's this block? The P block, right? These transition metals are all Ds, and then these down here, kind of like your grades. I'm just kidding. Ooh, just a joke. Leave Dwight alone. Okay, now how are these sublevels? On every energy level, you're going to have a different number of sublevels. On energy level 1, there is only one kind of sublevel, and helium, by the way, this electron actually belongs over here. We have the sublevel of S. On level 2, we have 2 sublevels, S and P. On level 3, we're going to have, how many sublevels? 3 sublevels. So I'm trying to show you the pattern. N is also equal to the number of sublevels. Now I'm sure you're asking, well, where is the third sublevel on energy level 3? It has to do with the fact that the D's and F's, if you remember, are under. So this guy starts on level 4, but when we get to the D's, does anyone remember what the set is? It's n-1. So this is actually start of the 3D line. The F's, if you don't know where to insert them, just look at the number, the atomic number. This is a 57, that's a 56, so it's inserted here. Okay? So it's on energy level 6 originally, but now it is 4 because it's n-2. So we have n-1 for the D's and n-2 for the F's. So on energy level 3, we have 3 sublevels. The S sublevel, the P sublevel, and then the D sublevel. Okay? Because this is energy level 3. Now, how many electrons can go on each sublevel? How many electrons on an S sublevel? 2. How many electrons on a P sublevel? 6. How many electrons on a D? 10. And how many on an S? 14. How many electrons can go in any one orbital? 2. So any one orbital can only hold 2 electrons. So we can also now figure out how many orbitals are in each sublevel. So on an S sublevel, there's only one kind of orbital, and it's spherical, 3-dimensionally spherical. Okay? So S only has one orbital type that holds 2 electrons, any S sublevel. Can anyone remember how many electrons are on a P sublevel? Electrons, sorry, I meant to say orbitals. How many orbitals are on a P sublevel? 3. So your P's, I don't know, they use the term dumbbell. I don't know how dumbbell they actually look. But there are 3 P orbitals that exist that make up a sublevel, and 2 can go into each orbital, so that's why we can fit 6 actual electrons across. 1, 2, 3, 4, 5, 6. All 6 of those will exist in the 3 P orbitals on that sublevel. Now, you're going to see in your book, and I don't want it to freak you out, names of these orbitals like PX, PY, PZ. Don't let it scare you. If you see a funny subscript, they're saying that's only one orbital. So how many electrons can go into PX? 2. How many electrons can go into PZ? 2. How many electrons can go on a P sublevel? All 6. Okay, so just watch the vernacular. The same thing that exists for the Ds. There are 5. We're not going to draw them all because they're all like these wacky, there's wacky clovers, there's this wacky thing with a donut-looking thing. We don't care, okay? But you just need another 5 of them, and their names are even weirder. One of them is dx squared minus y squared. And so again, yeah, really, and that's just one orbital and its name. So when you see those, don't freak out. Those are only single orbitals. How many orbitals on a d sublevel? 5. How many electrons on a d sublevel? 10. How many orbitals on an f sublevel? These are even crazier looking. 7. How many electrons on an f sublevel? 14. All right, good. So we remember some stuff from Chem 1. Yay. So let's answer these questions. Shell and level, same thing. So anytime you see shell, if you want to substitute the word level, that might help you in your head. What is the maximum number of electrons in a sub-shell or a sublevel in a 2s? All 2 means it's on the second level. Any s sublevel can hold 2 electrons. One thing I forgot to mention earlier, let's go back. I don't want to miss it for the video, is to talk about this n again. N, we said, was equal to the number of sublevels. So on level 4, we theoretically have 4 sublevels or 4 orbital types. Can anyone guess how I can figure out how many orbitals are on a level? How many orbitals are on level 1? 2 orbitals. No, on level 1 there's only 1 orbital. On level 2 there are 4. There's 4 orbitals, 3 p's and an s, right? On level 3 there's an s, 3 p's, and 5 d's squared. So n squared is equal to the number of orbitals on a level. L-E-V-E-L. Can anyone guess then how many electrons on a level? What would we have to do? Multiply by 2, because each orbital can hold 2 electrons. So 2n squared equals to the number of electrons on a level. And I told you that because it's going to help us answer a couple of these questions. What is the maximum number of electrons in a 3D sublevel? 3D sublevel. Maximum number of electrons? 10. How many electrons on an n equals 4? How'd you find 32? 2n squared. And then how many electrons in a 2p orbital? 2. Those of you who had said 6, hit your forehead. Any one orbital can only hold 2 electrons, right? Okay. And again, in the textbook, you might see, oh, 2px, or you might see 3dy squared, and you're like, what? That's just one orbital, okay? That's just all it is. So there's only going to be 2 electrons in that orbital. Okay. Hund's rule. I'm going to just draw out a little diagram to help you remember, but the importance of Hund's rule is Hund's rule says that you have to place electrons, or electrons build in a fashion where we're going to have the lowest possible energy. So if I were going to fill, do y'all recognize these? If I were going to fill this thing with 7 electrons, let's say, how would I place them? Up, down, 1, 2, and then how do I place them? 3, 4, 5, 6, 7. It's the filling the bus rule, right? If you were to go into the bus and on public transportation, nobody on the bus that you know, would you go and sit next to someone else? Probably not. Yes, really? I think people are weird. When I'm sitting on public transportation, like a subway or something, and someone sits right next to me and there's all these empty seats, I'm like, really? Go somewhere else, really. So for this, this is what Hund's rule is telling us. We have to fill them where we're going to have the lowest possible energy. Why is filling it like this not a low energy thing? I want to address this because we kind of just take it for granted because it's a rule. But why can't we do that? Why is that going to be a higher energy situation than this? Hold it down. Whoa, whoa, what's close together? Both of these are negatives, right? And so you're putting 2 negatively charged things in the same orbital. Remember, each box represents an orbital. So putting them in the same orbital, you're causing a bunch of repelling forces that really don't need to be existing at that point. At that point, we could just put the other electron here and then having it that way, we have a minimized energy, and that's why Hund's rule exists. Another thing I want to point out to you, and it's not, I want you to, when you're drawing these, do the traditional left to right thing, but just so you know, if I were to fill this, filling the S first, if I were to go to P's, there is no rule that says I have to fill the second one first. I can do this. This is legitimate. This doesn't change my energy standard. Remember, this is not, these aren't literally orbitals sitting next to each other. This is a visual representation of 3 boxes, each being an orbital, but remember how they are in space. These are the P's. So you got the PX, the PY, the PZ. I can fill either one first. It doesn't matter. So I'm not violating Hund's rule or Aufbau at all by doing this. Does that kind of make sense? However, we'll talk about Aufbau in a minute. However, when you're filling them on the AP, go ahead and fill left to right like you're traditionally taught. All right? I just want you to know that this is not a violation. This is actually okay. There is no energy difference between putting this electron here or here first. Bless you. All right. Let's move on. Now, Aufbau principle. For those of you in German, Aufbau, Boyer, anyone know what that means? Not bless you, not Gesundheit. It's a basis of the word to build, building. So the Aufbau principle states that protons are added. As the protons are added, electrons are added one at a time from low energy to high energy orbitals. All right. When we do electron configuration, we are following Aufbau's principle when we follow our finger across the periodic table to do electron configuration. So let's remind ourselves how to do this. You look at the total number of electrons in oxygen and you find where it is on the table. You're going to start from the beginning and you're going to first list the first energy level. Then you're going to list the sublevel and how many electrons are in that sublevel, 1s2. Then we're going to go to the next energy level, so we have to state it, the new one, 2. We go across the S's, S2. Whenever you change sublevel, now we're going to the P sublevel, you have to restate the level. So now it's 2P, and then we count over 4 to get to oxygen. Yes? For ones that are further down the periodic table, can you use the shortcut? Yes, I'm going to show you it's called noble gas configuration. Some people call it shortcut. Some people call it core configuration. The only problem with that is on the AP, they will expect you to be able to do both. I graded a question 2 years ago where the problem said, for the following, I think it was iron actually. No, it wasn't iron. It was iron was later in the problem. That was an ion question. But it was like sulfur or something. It said, write the full configuration, and then it had parentheses, 1s2, 2s2, ... Right? Over 90% of the people did shortcut. So in the situation like that, I don't know what else they were supposed to say to make you do the long way, so just watch yourself. You can do it unless you're told not to do it, okay? So we're going to practice this in a minute. I just wanted to revisit the whole concept of the Aufbau principle, building in order. So a violation of the Aufbau principle would be like 1s2, 2s1, 2p4. Do you see why that would be a violation? Because, right, we didn't fill that S sublevel before we went to the P's. So is that possible? Sure. We can hit this atom with a ray of light or visible light or put it in a flame, and the electron can get excited, and this is an excited state. When the electron falls down, maybe we get some color. Okay? All right. Orbital diagrams, before we get big into electron configuration, is drawing out the boxes, like I showed you earlier, and we're going to fill them with electrons. An S is just going to be one box, and underneath that I want you to write the sublevel. So here is another S. It's just on a different level. How many boxes am I going to draw for the P's? 3, because that represents the 3 orbitals, and I'm going to write 2p under them. Now I'm going to go ahead and fill them with the electrons from the electron configuration. How many electrons in the 1s? 2. Now if you want to draw full arrows, you can. If you want to draw them like this, whatever, it doesn't matter. I just do this the other way because it's faster. And then how do I fill these 4 P's? 1, 2, 3, and then double up 4. Okay? All right. What was the rule again that talked about these have to be the same spin and then double them up? Hund's rule. And I didn't mention that they do have to be the same spin. We want all of these orbitals to have the same energy. So having a flipped one would be an excited state. Say that again? Pauli's exclusion. We'll talk about that on Thursday. Yeah, Pauli's exclusion principle has to do with quantum numbers, and we're not doing quantum numbers this year is another story. All right. Another thing you need to be able to do is determine valence electrons. Valence electrons are the electrons on the outermost energy level. So in this little electron configuration, how many valence electrons do I have? 8. You go to the highest level. Here and here is your highest energy level. And then you look at how many electrons. We had 2 there and 6 there. That's 8. Looking at the periodic table, you can also tell valence electrons basically by what group you're in. Group 1, I'm looking at Roman numerals, 1 valence. Group 2, 2 valence. Over there, Roman numeral 3 is 3 valence, and so on. All right? Notice that we're only looking at main group elements, meaning the S and P block. Will D or F ever be valence electrons? No, they won't exactly. They will never be valence because, remember, as we go through, we always drop a level when we get to the Ds, and then we go back up to the 4s. Like here, 4s2, 3d10, 4p6. These are a level lower, so that is not part of our valence. Only S's and P's. That's where the whole concept of, an octet came from, because how many total electrons are in S's and P's? 2 in S, 6 in P's. 8. Yay. Okay. So this is just the electron configuration. So I want to do a couple full out, and then I'll let you do the shortcut. But let's go ahead and do the full sulfur. I want you guys to be loud. I want you to sound like you're chanting like you're in a cult. And let's do this. What? No, it's not. They didn't hear you. It's very hard to hear, and I'm glad it's not on the video, because I would have to edit that out with like a bird or a chirp or something. All right, here we go. Starting from the top. 1. Very nice. How do y'all feel about that? Let's do it again. And I'm going to take my mic off this time. And I am going to hold it out to you guys so they can hear you. We're going to do barium. It's really, really far down there. It's going to be a long one. But I want you to take it slow. I don't want you to go so fast because people at home need to write this down. All right. Nice and easy, and don't mess up. Go. 1 S2, 2 S2, 2 P6. 1 S2, 2 S2. Going to have you probably not do this again? No. I will allow you to use the shortcut or the noble gas configuration. So let's do that for EU. Notice where EU is located. It's on the first line of the S, okay? Where is this inserted? It's on 6, right? So when you do shortcut, you go to the energy level, the noble gas on the energy level above, which would be xenon. So we're going to put xenon in brackets. Why is it okay for us to do that? Why do you think we pretty much can ignore all the other electrons? Well, they're all full, but so? They're not what? They're not valence. What's important about valence electrons? They're the ones that react. They're the ones that are gained or lost when you make ions. So they're the ones that are in play. The rest of them are core electrons and just kind of hang out. So we have xenon, and then it's 6s2, and then 4s7. Okay? All right. I'm going to make sure this recording is still going. I'm a little nervous. Yeah, looks like it still is. Okay. let's go on to the next page. Do we need to do any more electron configurations? Let's do the shortcut for krypton at least. The shortcut. You can't just bracket krypton. Nice. Nice try. We can't do that though because, hold on, I'm going to give you a reason. We need a description, a detailed description of valence electrons. And by putting krypton in brackets, you're not describing valence electrons. So we're going to put argon in brackets and then 4s2. 4p6. All right, so how many valence electron in argon? 8. 8 valence. Let me ask you this. How many valence electrons do the transition metal have? All transition metals. For the most part, there is an exception, but yeah, most of them have 2. Why is that? Because, remember, we have the blah, blah, blah S2, and then the blah, blah, blah -1. D, whatever. So this is never valence. This is always going to be on your highest shell. So the valence electrons for all transition metals is 2. We have a couple exceptions we're going to talk about here in a sec, but for the most part, that's the case. All right, moving on. Ba-bam. Using the element silicon, show an orbital diagram. So that's the spinny thing. I'm just telling you right from the get-go, you're going to want to show your noble gas configuration, electron configuration, before you draw anything, because it's going to save you and it's going to make you, it's going to be easier for you to tell things from the electron configuration. So what is the shortcut for this? Neon. 3s2, then what? 3p2. Ooh, Dwight. Dwight. Woo. All right. Now, so looking at this, what? We need to now draw the orbital diagram. So I am 100% okay with you guys just drawing beyond the noble configuration. So I'm good with you just drawing this. Yeah, they usually don't. They have you interpret those more than draw them. But yeah, I'm sure they'd be okay with you just drawing that. So unless they say draw the full one. All right, so how many, we're going to go ahead and label our boxes with our sublevels. How many electrons in the first box? 2. How many electrons in the P's? 2. How do I place them? Up and up. Okay? All right. Now, there's new terms, paramagnetic and diamagnetic. You're going to look at a series of videos where we'll talk more about it. But ultimately, oh, Laura, I've got a job. What does the prefix di stand for? 2. All right. So, well, it's still a root. Di means 2, right? So, a substance is diamagnetic if all electrons are paired. If all electrons are paired, it is diamagnetic. If there are any one or more lone electrons in an orbital, then it is paramagnetic. So this has a couple lone electrons, right? By lone, I mean in this orbital, I only have 1 electron. In this one, I only have 1 electron. Those are not paired. Therefore, this is a paramagnetic species. Yes? Absolutely. Paramagnetic species are the ones that are going to be magnetic, because what happens, and this is a very, very rough explanation, if you think about this thing's ability to possibly share with another substance, share that orbital, they're not necessarily physically bonded, but it's kind of like a temporary holding spot where those things can come together and move apart. I actually got a gift. It's pretty cool. Yeah, did you already play with this? This is a ferrofluid, and this is a hematite-based liquid which has iron, and iron is paramagnetic, so it has magnetic properties. You're going to see tomorrow that paramagnetic stuff are things that are colored. Species that have ions that are colored in solution, those things are also paramagnetic. But I'm going to pass this around. Just look at the fluid as it is and then hold the magnet to it. and watch it, stick to it, and then you can look at all the spikes that it forms. It is super, super cool. Please don't drop this because it's a present for writing recommendations. And it was a very timely present because I just got it, and we're actually talking about it. So quietly look at that as we continue. I'm moving on with the lecture. Everyone will get a chance to look at it. Don't drop it. Moving on. All right, this is important. We have some exceptions in electron configuration. I've got good news and I've got bad news. The good news is you guys are not going to be responsible for looking at copper or anything in the copper family, or looking at chromium or anything in the chromium family and going, oh yeah, those are the exceptions. It's going to be flagged on the AP now. They've taken that out. And so chromium family and the copper family, what do I mean by family? Everything under it, have weird electron configurations. A question, the bad news is you still need to know why. So a question you might have is them say, hey, copper's configuration you might think is this, but it's really this. Explain. That's what you're going to have to be able to do. So what I want to do first is write out the expected configuration for these guys. What is, we're going to do shortcuts. So what is chromium? Argon, 4s2, 3d4, and then copper is argon, 4s2, 3d9. All right, so this is not, these aren't really how electrons in chromium in the ground state exist. So what I'm going to do is draw the little orbital spin for you to see. All right, so we expect it to look like this, right? Correct, yes, no. What actually happens, this one electron here, and I'm going to put a big X through it, goes there. Can anyone tell me, nothing happens in science unless it's energetically favorable. Can anyone tell me what that did to help the energy, to help lower the energy? Didn't stabilize? No, because valence, remember, those S's are the only valence. What did you say? A partially full D level. The core electrons, close. I want you to focus more on the little guy that I moved. He's the one you helped out. What did you do to him? He's no longer with another electron, right? So this little 4s guy now is going to be here in his own orbital, and repelling forces have been eliminated. Now, hold on. This can only happen between S and Ds because it's a very, very small energy gap here between those two. It's like a little boop down a stair. It's super, super easy. I don't want you to think this can happen between S's and P's. If I have this, I can't move this guy there. The energy difference between an S and a P is like me jumping across the Grand Canyon. Can't do it. Okay? So this can only happen because it's a positive thing in energy. Now there's another draw for this little guy. Look at these numbers. Why would this guy maybe like it here better again? What does more stable mean? Lower level, what does that mean? Why would a negative electron want to be at a lower level? A little bit lower. Closer to the positively charged nucleus. So not only is this guy going to experience less repelling forces, he is now also only a little bit, like a step, closer to the nucleus. Yes? Oh, it can. Oh, well, 3D3, 3D2, it has to do, there's way more chemistry involved in that. That has to do with what we call the degeneracy of these orbitals. These orbitals all kind of have a tendency to need to be at the same energy level. And by having different numbers in different places, it's not. So this commonly occurs between the S, and when we're filling out a sublevel. Okay? All right. Let's look at this one. This one's a little bit less, in my opinion, clear-cut, because there's only one thing dragging this guy back. So, again, I moved this guy to here. Well, hold on. I didn't go back. So what's the actual configuration? It's 4s, 1, 3d5. That's the configuration. So you want to hear something that's going to blow your mind? I heard earlier in an earlier class, I was pretty impressed. Someone said, so copper or even chromium, because this other one is also 4s1 3d10. Copper here, looking at copper, because we already know something about copper. How many valence electrons does it have then? 2 or 1? And my answer was both. What can you tell me about copper? It has 2. And what are those charges? +1 and +2. When it's +1, it loses 1 electron. When it's +2, it loses 2. Isn't that cool? All right, but anyway. So when this electron moves here, 4s and 3d, a lot of students are like, well, why is that happening? Because it's going from repelling forces to repelling forces. The only thing that's positive here for this little guy is that he's a little bit closer to the nucleus. Okay? So just know that this happens in the families where we have a 3d4 and a 3d9. But you will be told on the AP, hey, this is an exception. You don't have to remember that it's an exception. Make sense? Last year you did because on the AP you did, and so I assumed this year it would be the same, but it's not. Yes? No, you won't have. They're not going to ask you, Andrew, what's copper's electron configuration? They're not going to do that to you. No, I'm not either. However, they will say, hey, copper's not S2D4, it's S whatever, chromium, it's S1D5, explain. Yes? So does it have anything to do with the fact that it's half full and all full, or not really? Half full and all full, and this is a misnomer. Your textbook might say this orbital is more stable because it's half filled. The AP doesn't like that as an explanation. Why is more, it's not an answer. Why is half filled more stable than full? Why is one electron more, we already talked about it, because it's repelling forces. So by saying it's half filled, it's not enough of an explanation on the AP. They won't take it. All right, last thing of the day. We only have 6 minutes. This is a long recording. Write the configurations for the following. Now, this is really easy to do when you're dealing with your main group elements, but students always mess up the transition metals. So I'm going to pretty much insist, whenever you're writing the core is the shortcut, by the way. Whenever you're writing electron configurations for ions, I want you to write out, and I'm going to be mean about it, I want you to write out the neutral first. Write out the neutral first, and then we can charge it. So sulfur is neon, and then what? Yes? 3p4. Okay. Now, for sulfur to become a -2, what has to happen? It's going to gain 2 electrons. So we're going to put those electrons right there because this is valence, and we're going to put them in there, and we're going to get neon 3s2, 3p6, and that's S-2. What noble gas is that isoelectronic with? Argon. Isoelectronic means it has the same number of electrons. So you're kind of writing the electron configuration for argon, right? That's easy. What about aluminum? Aluminum neutral is neon 3s2, 3p1. So for it to become a +3, what has to happen? Add? Subtract how many? We're going to lose that, and we're going to lose that. So we're really looking at the electron configuration for neon. You can't just leave neon in brackets. We've got to drop it down. If you want to write helium, 1s2 would have been the same amount of work writing. 2s2, 2p6 then would be your configuration for aluminum +3. This is the most important one. And this is one that was on that same test 2 years ago. And I don't even know how many, I think maybe a handful out of the 800 tests I grade got it right. So looking at this, iron, its core is what? Argon, and then what? 4s2. How many across? 5? 6. 3d6. Okay. What do you think? Okay, if we need to be a +3, we're losing 3 electrons. What do you think everybody did? Took away 3 and did 4s2, 3d3. Wrong, wrong, wrong. Why is that wrong? They're not the valence electrons. We have to lose those first. So we end up getting a configuration of, for the two S's go away, then we lose another D. So we get a 3D 5. Okay? It's a 3D 5. Nope. Nope, no S's. Because those are now gone and donated and are going to be somewhere on some other ion, making another ion negative. Now, this is also really cool. So let's look at this. I want to show you this. And you can pretty much rationalize something like this for every transition metal we've done. What are the two possible charges of iron? I might ask you, hey, justify that. What would make iron be a +2? Look at this. We'll make this one the +2. We just lose our valence, right? If we just lose our valence, bam, +2. Why is iron a +3? It's going to lose these guys and this one that's got repelling forces. That's why iron is more commonly +3 than it is +2. +3. So every single multivalent we have, you can find a way to justify it using the electrons. It's really cool. All right. Question?
I just don't really get how Fe +3 turned into the argon 3d5.
Okay. Fe neutral has this electron configuration. Do we understand that? Okay. So for it to become +3, it has to lose 3 electrons. The first electrons that are lost are the electrons on the outermost shell. This is a 4, that's a 3. So it has to lose those first, and then it loses one of those guys. All right. Good work.